do I hear myself? I don't seem to be getting audio that way either. Oh, there we go. Now it's coming in. Okay, it just took a few seconds. Just a bit of latency. Okay, next order of business is checking to see if our camera feed is working. All right. Usually it only takes like 5 seconds between me saying or doing something and it showing up on the screen, but it looks like it's a bit more laggy today. I wonder why. Well, the important thing is we've got things up and running, so let me go ahead and put away my headphones. This is why, ladies and gentlemen, I always do my audio checks. In case anybody was feeling, frustrated by my tendency to do this when nothing goes wrong, today I grant you a day where things went wrong. But the good news is that we don't actually have that much left to cover today. So I realized when I was timestamping the previous 2 streams, I realized that I already have a video from last year that covers a lot of problems that I was planning to cover today, so maybe I'll repeat some of them, but I'll just refer you to that video anyway, and maybe I'll find some different ones to do. Maybe I'll mix and match. We'll see. We'll figure it out as we go. But in terms of mission critical stuff that we need to cover, there's not much left. We just have Kepler's laws, a few examples, and that's it. So without further ado, let's begin. The backside of this is already used, so yeah, we'll start with a fresh new sheet of paper. And sorry for postponing this multiple times, but hey, I sacrificed my gaming stream for this, so you're welcome. Well, actually, the gaming stream wasn't going to happen anyway because of things that I didn't catch up on in-game during the past week, so yeah, I figured I might as well take advantage of that. And speaking of scheduling, might as well talk about this real quick. I do have another stream scheduled for tomorrow and another one scheduled for Sunday. I might postpone one of them, so it might either become Saturday and then move the Sunday over to Monday or Tuesday, or I'll skip the Saturday, do the Sunday, and then do a Monday or a Tuesday. But either way, between now and Tuesday, my goal is to have 2 more streams in addition to this current one. That's the goal, and those 2 streams are going to be, if you saw the titles already, they're going to dig into rotational kinematics, and then the next one after that is going to dig into the topic of torque. But yeah, torque should be covered by Tuesday if things go according to plan, which maybe they won't, because you've seen how these past few weeks have been just kind of all over the place with the schedule. Can't help it. Sometimes my students have tests and are texting me at random times of the day with their questions, and apart from working with students, I've got other life stuff going on. But anyway, that's enough of me rambling. Let's figure out what we're doing today. So today we are going to discuss Kepler's laws, which are focused on the motion of planets, but they can also be applied to the motion of, for example, satellites, moons revolving around planets, not just planets around stars. It can work for either case. So Kepler's laws. Without further ado, let's begin with Kepler's laws. So Kepler's laws, we've got 3 of them. And the first 2 are just conceptual more than anything. I mean, I guess there is like a mathematical proof for them, but that's beyond the scope of the course. You won't do this in Physics 1 or even Physics C. I didn't learn the deeper details of this until like a 3rd year college level physics class. So yeah, it's not something that would be appropriate to include on the AP exam or in an AP course in general. So Kepler's first law, very simple. It says that all planetary orbits are elliptical in shape, not circular. We're still going to treat them like they are circular because the elliptical case, again, is the math is more complicated. We don't have the tools to deal with it. All planetary orbits are elliptical with the star, in our case, the sun, at one of the foci of the ellipse. So in case you didn't learn this in your pre-calculus class, there are 4 different conic sections, as they're called, and they're called conic sections because you can take a double cone. If I draw a double cone, and then I take a flat plane and I cut through it at different angles, there are 4 different shapes that I can get. So let's pretend this hemisphere here is a cone. I know it's not pointy, but let's pretend, just for the sake of illustrating the different sections real quick. So if you cut through it vertically, then the shape that you'll get when you cut this double cone vertically, the shape you will get is something called a hyperbola. And its graph will look like this. It'll either be a horizontal hyperbola, like this, where this is your x and this is your y, or it could be rotated 90 degrees. It could be a vertical hyperbola. That's called a hyperbola. You already know one of the other shapes. If I cut at an angle that is parallel to the sides of the cones, if I cut this way, so that's not really going to show well on this hemisphere, but if I cut at just the right angle, then the shape I will get in that case, the shape of the slice, the shape of the intersection, is going to be a parabola, which you should be familiar with. We've used that term a number of times. In fact, I think we used it last time, if I'm not mistaken, when we talked about the shape of the path that you can get from projectile motion versus uniform circular motion. You get a parabola. Just the graph of a quadratic function. Parabola. If you cut it horizontally, if you cut this way, then the shape you get is a circle. And the shape you get is a circle. And the fourth conic section that you can get is an ellipse. The fourth conic section is an ellipse. It's a stretched circle, you could say, or squished, depending on how you want to think about it. That's what happens when you cut it at any other angle. When you cut it at any other angle, you get something that's just sort of not quite circular. It could be kind of like with the hyperbola. It could be a vertical or horizontal hyperbola. Come to think of it, same thing for parabolas. You could have horizontal parabolas. But yeah, this shape is an ellipse. And each of these conic sections has one focus or two foci. The word foci is the plural of the word focus. One focus, two or more foci. You actually know this form of pluralization because you've heard words like radius, whose plural is radii. Or maybe when you first go to a new class on the first day of class, you have a syllabus, whose plural is syllabi. So a lot of words that end with us singular, you just replace the us with an I to make it plural. That's your mini English lesson of the day. So don't get overwhelmed by this word. Anyway, an ellipse has two foci. An ellipse has two foci, and the neat thing about an ellipse, this is an experiment you can do at home. You can take two, I don't know, pegs, hooks, pens, nails. If you have just a random piece of wood and you just drive two nails into it, and then you tie a piece of string around the nails, and then you tie a pencil to that string. Or you don't tie it to the string necessarily, but you just let the pencil kind of be guided by the string. Let me see if I can illustrate this. I should have something string-like I can use here. Okay, so let's say I use this thing, and let's say I have just that much length of string, and let's say I have it nailed down in two places. How am I gonna show this? Do I have anything I can use that can stand? I don't think so. Well, the idea is if you take this piece of string and you tie it between these 2 points loosely. It has to be loose. It has to be, your string has to be longer than just the distance between these 2 points. It has to have a little bit of give to it, at least a little. And then what you can do is you can try and force your pen or pencil to trace out the shape. If it was tied to a single point, the farthest you could go is going to be fixed and you just have a circle. But if it's tied to 2 points, then the shape that you trace out is going to be this ellipse. So for example, maybe my pen reaches this point and then I swing it around and say at some point it's over here and the string is over this way. And maybe at some point as I continue tracing, my pen ends up here and the string will end up looking like this. So what I'm saying is, let me do this in red. What I'm saying is, if you take this length plus this length, that's the total length of the string. That is the same as the sum of this length plus this length. And I would draw that third one, but it's already looking kind of crowded and hard to interpret. But yeah, that's something unique about the ellipse. That's actually how an ellipse is defined. It's the wording of the definition of an ellipse eludes me, but basically it's the set of all points where the sum of the distances of each point from the foci is constant. Again, the wording is not very easy to digest the first time you hear it, but conceptually, I hope my idea with the pen tracing got through. You can, again, try this at home, find some way, maybe, get a friend to hold down the string if you don't have nails and a plank of wood. But yeah, just find a way to hold down the string at 2 points loosely, and then try and use a pen or a pencil and trace out the shape that the string will allow you to actually reach with your writing utensil. It'll be an ellipse. Anyway, these 2 points, these foci of the ellipse, I'll draw a new one just so that it's easier to talk about. These 2 foci are going to be on an axis of symmetry. So the ellipse, in addition to having 2 foci, of course, like the circle, it has a center. And the distance from one focus to the center is equal to the distance of the other focus from the center. And Kepler's first law says that the orbited object, the sun in case of the Earth and the planets within our solar system, the Earth in the case of our moon and any satellites that we have up there, that orbited object is going to be at one of the 2 foci. What's at the other focus? Nothing. Just empty space. But Kepler's first law says that one of the foci is where one of the orbited objects will be. And we don't actually have uniform circular motion. Instead, we have this, well, it's cyclical motion. It's consistent and it repeats. So there's that. There's some sort of order to it. It's not completely chaotic, but it's not uniform circular motion. It's not constant speed. It's not constant distance from the center. So you'll have, for example, when you're at the farthest point, let's say this is the Earth, when you're at the farthest end of this ellipse, when you're the farthest you can be from the sun, during that time, the Earth is actually moving at its slowest. During that time, the Earth is moving at its slowest. And then let's say it's cycling this way. Let's say we're going clockwise. And so once it gets to this point, it's at its lowest speed, which is not 0, but it's just the minimum. And it gets pulled by the gravitational force, right? The force of gravity on the Earth would be, at this point, it would be just straight in that direction, but because the Earth already has some velocity this way, it's not going to just go straight into the sun, it's going to turn. A concept we understand from uniform circular motion. So it turns and it starts speeding up because once it gets to this point, for example, the force of gravity is this way and the velocity is this way, not quite perpendicular anymore. Now there's going to be some component of this force is parallel to this velocity and will cause an increase in the magnitude. So when you're over here, you're still turning, but you're also gaining speed. And over here, still turning, gaining speed, turning, gaining speed. Once you get around this point, now the force of gravity is this way, while the speed is this way. Now you're gonna start slowing down. Now the Earth is getting faster and faster. At this point, the Earth is at its fastest, at this point, the Earth is at its fastest, and once you're past this point, oh, then I guess what I said earlier is incorrect. You're still gaining some speed over here. And once you get to here, that is when you stop gaining speed. At this point, the force of gravity is this way, the velocity is down this way. I probably should have used different colors for each because this drawing is getting hard to follow. And now the Earth starts turning back, and as it turns back, now the force of gravity is going to have a component that's pointing slightly backwards compared to the velocity of the Earth. So now it's beginning to slow down, and once you get to here, it's easier to see. Once the Earth is over here, its velocity is to the left, the force of gravity is, I guess, in our drawing, up and to the right. That rightward component is tugging on the Earth, slowing it down. And the cycle just repeats from there. So it's kind of slow, speeding up, speeding up, speeding up, fast, zips past, slows down again, slows down, doesn't quite grind to a halt, and then starts speeding up again. And that is the true nature of planetary orbits. As for the math behind it, you'll have to wait until a later physics course in order to learn that stuff. But you just need to conceptually understand those things. I've seen on the AP exam, I've seen them ask questions where it's simply pick the correct diagram. Like it would be a multiple choice, and it would be pick the correct diagram for where the sun would be in this illustration of an orbit, or pick the location, and they'll have different locations on an ellipse marked A, B, C, and D, and they'll ask you, at which of these points is the Earth moving the fastest? And I guess choice E would be none of the above or not enough information or something like that, which of course would be the wrong answer. So you really just need to understand it conceptually, and that's it. And I guess you might be asked to draw this path. If it's on a free response question, you might be asked to just quickly draw a correct illustration of whatever it is they're asking for. The Earth at the point where it's moving fastest, at the point where it's moving slowest, or maybe it's not even the Earth, maybe it's the moon around the Earth, or one of Jupiter's moons around Jupiter, or whatever. You get the idea. But that is Kepler's first law. Kepler's second law, I've always found the wording of it to be rather confusing. It still ties into this whole ellipse business, and I'm going to draw an ellipse again. So, Kepler's second law says that a line connecting the star, or just orbited object in general, in our case, let's continue assuming that we're talking about the sun and the Earth here. A line connecting the sun and a point on the planet's orbit in our case, the planet is the Earth, or I guess it could be Venus or Mars or whatever, any planet from our solar system, really. A line connecting the star and a point on the planet's orbit sweeps across equal areas in equal time intervals. What on earth is this even saying? I don't know what the deal is with this chapter and poorly worded explanations. We had, was it last time or the time before, when we talked about the whole the Earth curves away business and how I don't really like that as an explanation of why the moon doesn't fall straight into the Earth. This one is next in line. Actually, I think this one is probably worse. Because at least the Earth curves away is simple wording that you might have a chance of understanding. But this is just, what on earth does sweeps across mean? That's not something you hear every day. So let me illustrate it, because I think illustration is better than words here. So you have an orbited object, let's say the sun. And you have the orbit of a planet, let's say the Earth. And let's say that you are at point A, and you move to point B, and the amount of time it takes for the planet to move from point A to point B is t, in days, years, whatever unit of time you want to use. It takes an amount of time t to travel from point A to point B. Now, remember, this is when the Earth is moving slower. This is when the Earth is moving slower, so this is a considerable amount of time. If you take any other pair of points that take t amount of time to move between, let's say, for example, over here, here's point C, and over here the Earth is moving faster, so in the same amount of time you would actually cover a greater arc length, a greater distance. So let's say over here you go from C to D, also in that same amount of time t. Also in that same amount of time t. Well, then Kepler's second law is saying that if you draw a line from the sun to point A, and then you just continue monitoring that line, the shape of the pizza slice that it traces out, for lack of a better term, this pizza slice, the area of this slice will be the same for points A to B and points C to D, as long as the amount of time it took to get from A to B is equal to the amount of time it takes to get from C to D. These pizza slices will have equal area, and you can kind of believe that when you look at the shape. Here, this one is less wide, but it makes up for that with its length, whereas this one is not very long, but it's pretty wide. Actually, the way I've drawn it, this one appears to have a little more area than this one. But if I had drawn it better, I think you would find it convincing. So that is the concept behind Kepler's second law. Not something we need to prove or understand mathematically, just something you need to know just in case they ask about it in a multiple choice question or whatever. So that's Kepler's second law done. Kepler's third law, we kind of accidentally did it, or at least we began it last time. There was, what was it? Let me see if I can find it. What did we do last time that almost got us Kepler's third law, at least like the beginning of it? Do I not have it? I think it was whenever I was trying to do... It wasn't the escape velocity one. Okay, I'm not finding it. I'm not finding it. Maybe I'm misremembering or something. Or maybe I lost that sheet. Anyway, Kepler's third law says, and this will be better understood as an equation, but we'll write it in words first. The square of a planet's orbital period, the square of a planet's orbital period around its star, in our case again, the sun, is directly proportional to the cube of the orbital radius, Actually, it's directly proportional to the cube of the semi-major axis length because it's an ellipse, but we're going to treat our orbits as being circular because, again, ellipses, we don't want to deal with the math of ellipses in this course. To the cube of the orbital radius. Okay, what does this mean? So period, we defined, was it last time? No, it was the stream before last when we first introduced uniform circular motion. We did a problem, and that was our introduction to the concept of period. Period is the amount of time it takes to complete a single cycle. In this case, a single lap around the sun, a single orbit. For the Earth, that takes exactly 1 year. So if you get a problem and it wants you to calculate the orbital radius of the Earth, and it gives you information like the mass of the sun, and then you go, wait a minute, they didn't give me the orbital period. How am I supposed to calculate the radius? The orbital period is common knowledge. It's exactly 1 year. You know how long a year is. At least I hope you do. It's not 365 days. It's 365.25 days. Because remember, every 4 years, we add a 29th day to February. It takes 365 1/4 of a day to complete an orbit around the sun here on planet Earth. 365.25 days. And you know how many hours are in a day if you need to convert it to hours, and you know how many seconds and minutes are in an hour if you need to convert to seconds or minutes. I will probably be converting to seconds in a lot of our calculations because seconds are kind of the unit that we prefer in physics a lot of the time. It tends to work best with our other already established units. So mathematically, what this is saying is the period squared, the time it takes to complete an orbit squared, is equal to some constant, times the radius of the orbit cubed. The square of the period is proportional to the cube of the radius. And this is something that the AP exam loves to take advantage of to create best fit line problems. They'll give you a problem where they give you a partially completed data table, and they'll give you like some graphing space. They'll give you like this grid, and they'll ask you to plot points. They'll give you a table. They'll give you here's radius, here's period, and then they'll give you some values over here. And then they'll probably leave these two spaces empty, and they'll say, you have these free columns for any additional data in case you need it. Wink, wink. Of course you need it. That's why they gave you the space. So you will add radius cubed and period squared over here, and you'll just take all of these values and cube them and copy them into here. And all of the numbers they give you here, you'll square them and copy the results into here. And then you'll make one of these, for example, you'll make this your t squared axis, and you'll make this one your r cubed axis, and you'll draw your data points. And then you'll find your best fit line. It doesn't have to be perfect, but what they look for on the exam is roughly half of the points above the line and roughly half below. And unless there is a good physical reason for it, they might make it a point to see whether or not you made sure to not force your line through the origin. Unless there's an actual valid physical reason why you know at r cubed equals 0, t squared equals 0, you can't do that. Because in real-life scientific experimentation, the best fit lines that we get from our observations are almost never that perfect. Even if it's supposed to go to 0, if you are doing a real-life experiment, that probably won't be the case, unless you have some way of directly measuring when one variable is 0, the other variable is 0. If your experiment, the way you do it, doesn't allow you to reach that conclusion, then you cannot have 0, 0 as one of your data points. So that is something they look for. And then, again, roughly half the points above your best fit line, which I guess I kind of violated because I've got 1, 2, 3, 4 above and 2 below. Let's fix that. There. Now I have 4 above and 3 below. So roughly half above and half below, and also the distances between the points and the line should be somewhat minimized, right? You want the line to be as close to the points as possible. Of course, if you have any outliers, like you get a random point over here, they would expect you to recognize that, but they probably won't do that to you because this is not a statistics course. They probably won't do that to you, but just in case, if you see one point that's just way far off, you can write that off as some sort of error or mistake if the other points seem to have a clear trend. But yeah, that's best fit line problems for you. They love giving you Kepler's third law as a best fit line problem. And then once you draw your best fit line, they'll ask you to use the slope of the line to figure out something. Usually they'll ask you to determine the mass of the sun. And the way that'll work is, well, the mass of the sun, as we're going to prove later, is a part of this constant. So the slope of this line will be equal to this constant, or 1 over the constant, depending on whether or not you flip around these axes. If you graph r cubed versus t squared instead, then the slope would be 1 over the constant. You just have everything flipped. But it shouldn't matter to you as long as you stay on top of your math. That should be no issue. I mean, it's just linear equations, I would hope, by this point in the course. And actually, if you reached the course in the first place, I would hope your algebra skills are good enough that linear equations aren't, going to be that much of a, what's the word I'm looking for? Are not going to deal that much psychic damage to you. At least that's what I would hope. But if you are worried about that, maybe go back and review linear equations. Maybe go back and refine your understanding of slope specifically. Anyway, let's go ahead and actually prove this formula and see where the mass of the sun, or just the mass of the orbited object in general, factors into all of this. We are going to assume a circular orbit. We are going to assume a circular orbit. And we'll say here is, I'll just call it our big M, our generic orbited object, and then our little m, which may not be so little, it could be an entire planet, but it is little compared to the orbited object. That's our orbiting object. So the orbiting object versus the orbited object. Very important to keep those two separate from each other mentally. Otherwise, you'll run into problems. Okay, so what forces are acting on this orbiting object? Well, there's only one force. When this thing is all the way in outer space, no air resistance because there's no air in space. No friction because there's nothing physically touching this orbiting planet or satellite or whatever. The only force is the force of gravity. And at those large distances, you want Newton's law of universal gravitation. So the only force on this object is the force of gravity. So the net force on this object is always pointing towards the center of the orbit. Well, how about that? And then the object will, of course, have some sort of starting velocity. And since our net force is always pointing towards the center of our orbit, what is that? That's a centripetal force. So net force equals force of gravity is a centripetal force, therefore it equals m times our acceleration is a centripetal one, so it's v squared over r. Okay, nice, but also our force of gravity is big G, mass of the orbited object, mass of the orbiting object, over the distance between their centers squared, the distance being r squared here. I'll draw r onto our diagram. Let's do that in pink. So here is r, the radius of the orbit. Well, would you look at that? The mass of the orbiting object does not matter. The mass of the orbiting object does not matter. This is something you will see over and over and over again when you do practice problems for this chapter. The mass of the orbiting object often cancels out. Okay, we can also cancel out 1 power of r. And that leaves us with v squared equals gm over r. Now, one thing we could do here, just a little detour, is we can now get a formula for the kinetic energy of this object. All we have to do is multiply by 1/2 of its mass on both sides. So actually, go back a step here and uncancel the m's we just canceled. We can say kinetic energy of the orbiting object is equal to 1/2 m v squared is equal to 1/2 m times g big M over r. Okay. And then the thing that we're actually trying to find is the relationship between orbital radius and period, not between radius and tangential velocity. So what do we do here? Well, you might remember when we did the Ferris wheel problem 2 streams ago, I believe, we wrote a definition for period when you're talking about circular motion. Period for circular motion, the amount of time it takes to complete one cycle, Well, actually we didn't. It's going to be 2 pi r over v, but that's not how we found it. So what we did was we said that the tangential speed is equal to distance over time. And if the distance is 1 full cycle, 2 pi r, then the time is, by definition, the period, the time for 1 full cycle. And then if you rearrange that, if you multiply by t over here and you divide by v, you get t equals 2 pi r over v. You don't need to memorize this. I did make that point the last time we did this. As long as you remember this process, you should be able to very quickly just go v is distance over time. If the distance is 2 pi r, the time is big T. You should be able to just quickly rederive that on the spot. You do not need to memorize here. I would much rather you actually understand this reasoning process instead. Anyway, I want to actually keep it in this form, v equals 2 pi r over big T, and I'm going to write that in over here. So g big M over r equals the square of 2 pi r over big T. That's going to be, the square of 2 is 4, the square of pi is pi squared, the square of r is r squared, the square of big T is big T squared. Oh, now it's starting to come together. If I multiply the t squared over to the left, and I multiply the r over to the right, then I get t squared big G big M equals 4 pi squared r cubed. And then if I divide by gm, then I get t squared equals 4 pi squared over gm times r cubed. Now it's either this or the reciprocal of this. This is something that I never remember, that is called the Kepler constant of the orbited object. Okay, yeah, it's the 4 pi squared over big G M. So this thing over here is called big K. Again, you do not need to memorize this. Wait, I just copied it. Let's try that again. Big T squared equals K, big K, times r cubed, where big K is the Kepler constant, is what we call it, the Kepler constant of the orbited object. So if the orbited object is the sun, we will call this K sub capital S for sun. If we're talking about the moon around the earth, we would have big K with a subscript of capital E for earth, and so on and so forth. We would have K sun is 4 pi squared over mass of the sun. K earth is 4 pi squared over mass of the earth. I suppose if you're working for NASA, you probably have these constants written down somewhere in a data table or whatever, but for our purposes, for AP Physics, you don't need to deal with this. You don't need to remember this relationship. And even if you did, you can just go through this derivation process. Just start from Newton's law of universal gravitation and uniform circular motion. Combine those two relationships and just go through this process. Remember that V is 2 pi r over big T. And I would actually advise that you go through this process multiple times. Like, wait a few days so that it's not completely fresh in your mind, and see if you can reprove Kepler's third law again on your own, and then maybe give yourself like a week or so to forget and try it a third time. I made my students go through this derivation multiple times. Like, I would see them once or twice a week, and I would, for 2, maybe 3 weeks, just keep having them redo the derivation. And they saw my point, because whenever I would ask them to redo it, they would forget until the third or fourth time when they would finally remember and do it with confidence. And yeah, knowing how to go through that reasoning process is much better than trying to just memorize the outcome. So yeah, this Kepler constant thing is, I guess, what you would get if you graphed t squared versus r cubed and did a best fit line. And it contains the mass of the orbited object. So if you drew your best fit line and then you calculated your slope, you took 2 points on the line and you just did, your delta y over delta x and calculated the slope that way, you could then set it equal to 4 pi squared over big M and then solve that result for big M. So I guess you would multiply the big M over to the left, divide by the slope that you got, 4 pi squared over whatever slope you get is equal to big M. So they would probably ask you, if this was an AP free response question, they would probably say, use your best fit line to calculate the mass of whatever, Jupiter, if they're talking about the moons of Jupiter and their orbital radii and periods over here. Use your best fit line to calculate the mass of your orbited object. So yeah, that's Kepler's third law, proven. Now there's another version of Kepler's third law which has some interesting uses. There's another version of Kepler's third law which has some interesting uses. And that other version is this. If t squared equals a constant times r cubed, if t squared equals a constant times r cubed, then that means the ratio t squared over r cubed is constant. T squared over r cubed equals a constant. Assuming, of course, that you're talking about the same orbited object, because remember, the orbited object determines this k. K is not like some universal constant. It's a different constant for different orbited objects. It's different for Jupiter, from Earth, from the Sun. They all have different k values. But assuming you're talking about two different things orbiting the same third thing, so for example, 2 of Jupiter's moons orbiting Jupiter, or a pair of satellites orbiting the Earth, or a pair of planets from our solar system orbiting the Sun. As long as we're talking about two things that are orbiting the same third thing, as long as those two things are orbiting the same third thing, then you can use this relationship to quickly determine, if you know 3 pieces of information, you can quickly determine a 4th piece of information. So you can say period squared over r cubed for Earth, for example, period of Earth squared over orbital radius of Earth cubed. If that's equal to k of the Sun, then similarly, the period of Jupiter squared over the orbital radius of Jupiter cubed, that must also be k of the Sun, which means they equal each other. So t1 squared over r1 cubed equals t2 squared over r2 cubed. It's very easy to get your subscripts and your exponents mixed up here because, you've got exponents of 2, but you've also got subscripts of 2, so that can really mess you up. So be very careful when writing this. If you prefer, one way to avoid screwing this up is you can just call this A and call this B. I think that helps reduce the confusion. Ta squared over Ra cubed equals Tb squared over Rb cubed, where A and B are two things both moving in orbits around the same center. So you can't use this relationship between, say, the moon around Earth and then Jupiter around the sun. It doesn't work that way. You have to compare two things that are orbiting the same center. It only works for those cases. So be very, very careful with this. But as long as you keep that in mind, this gives you a convenient shortcut for determining things like how long is a year on Mars, for example. Let's actually do that as our first worked example of this stream. So let me look up the distance between Mars and the Sun. So the distance from Mars to the Sun is 2.28 times 10 to the 11 meters. So our Mars is 2.28 times 10 to the 11. 2.28 times 10 to the 11 meters. The distance, average distance, really, because, again, the true orbits are elliptical, so the distance from the sun is constantly changing as time goes by. But the average distance, which we will take to be a radius since we're assuming a circular orbit, the average distance between Earth and the Sun is 1.496 times 10 to the 11. That number should look familiar. We did use it for an example in the previous stream. And then they want you to calculate what is the period of Mars. What is T Mars? You do not even need to know the K value of the Sun. You don't even need to know the mass of the Sun for this type of question. All you need to remember is TA squared over RA cubed equals TB squared over RB cubed. And of course you can rearrange this equation in multiple different ways. You can also rewrite it as, you could flip both sides and make it RA cubed over TA squared equals RB cubed over TB squared if you prefer having the radius terms in the numerator instead. You could do RA cubed over RB cubed equals TA squared over TB squared. There's a bunch of different things you can do with this. If you just if you cross multiply and do a bit of algebra, you can rearrange this equation into whatever form you prefer. But yeah, this is all the information they give you. Is this enough information? Yes, because you have the power of common knowledge. You have the power of common knowledge. You know what T-Earth is. T-Earth is 1 year. 1 Earth year. And actually, the nice thing about this equation is that you don't have to be too particular with the units. As long as one pair of units match, then your unknown will come out in the same units as its other corresponding unknown. That's probably not the best way to word that, but I guess what I'm saying is if you're calculating a time, if you're missing a time, and your orbital radii are in the same units, then whatever units of time you put in for the other object, those are the units of time that will come out. So if I keep T-Earth in years, I will get T-Mars in years, Earth years. If I convert T-Earth to days, then I will get T-Mars in days. If I convert to hours first before plugging into the equation, T-Mars will come out in hours. And of course, if I go all the way to seconds, then I will get T-Mars in seconds. Now, seconds are going to be a ridiculously large number, so you will probably need to convert back to something more reasonable, like days, months, or years. Well, I guess months aren't really consistent. I mean, some people will say a month is 30 days, but yeah, maybe not months, but days or years. is probably what you're going to end up converting your final times to, just so that you have something that's, comprehensible. Because if I say however many bajillion seconds, that's not intuitive. You don't have a real sense of how much time that is until it's converted properly to a more appropriate unit. So let's go ahead and work this problem. My calculator gave up on me the other day, so we'll see if it's still functional today. So far, so good. I've got... I guess another thing I could do is these don't have to be in meters as long as I convert them to the same units. As long as I don't even need units at all, I just need the ratio between them. So if I do 2.28 times 10 to the 11 over 1.496 times 10 to the 11, I can just do 2.28 over 1.496, and that's 1.524. So R Mars over R Earth is equal to 1.524, roughly. Now, this is something that we actually use. The distance from Earth to the Sun, this is known as a distance that we call 1 AU, 1 astronomical unit. 1 Earth distance from the Sun. Well, average Earth distance from the Sun. So if the Earth is defined to be 1 astronomical unit away from the Sun, then I guess Mars is going to be 1.524 AUs away from the Sun. It makes sense that it's greater than 1 because Mars is further away from the Sun. If you did this for Venus or Mercury, you should get something that's less than 1. I don't know, 0.7 or 0.6 or something around there maybe, or between, or maybe even less. Who knows? I don't know those numbers off the top of my head. But yeah, if you see astronomical units in your textbook problems, don't be alarmed by that. It's just a distance unit that is convenient when trying to calculate distances in outer space. That's all it is. It's just 1 Earth distance from the Sun. Okay, so I will actually go ahead and do this in astronomical units then. So period of Earth squared, so 1 year squared over 1 astronomical unit cubed. Oh, well, isn't this nice? 1 over 1 equals T Mars squared over R Mars cubed over 1.524 astronomical units cubed. Okay, so I get astronomical units cubed cancels with astronomical units cubed, and this is why it doesn't matter what units they are as long as they agree with each other. And we can already see once I multiply this 1.524 cubed over to the left-hand side, I didn't mean to cross out the cube with it. That's supposed to stay because it still affects the 1.524. But yeah, if I do 1.524 cubed and then multiply it over to the left-hand side and then square root it, that gives me the period of Mars in years. 1.524 cubed is 3.5396. So I'm going to go ahead and multiply it over. So 3.5396 times years squared equals T Mars squared. And then if I square root both sides, square root of a year squared is going to be years. So square root of 3.5396. I'm getting about 1.88. So T Mars is 1.88 years. So a year on Mars is about twice as long as an Earth year. Almost. Almost, but not quite. Think of all the amazing things we could do if we had that kind of time in a year. I mean, it's not like being on Mars magically just gives you more time. You would age at the same rate anyway. Actually, you might be worse off on Mars because the gravity there is weaker, and you've probably heard about how astronauts need to work out regularly in outer space, or else their muscles will atrophy due to the lack of gravity that forces their muscles to exercise. If you don't use those muscles, then yeah, they'll just get weaker. So astronauts, before coming back home to Earth, if they're not exercising consistently, they will have a hard time managing even walking when they get back on Earth. And you thought sailors had it bad. Okay, what do we want to do next? I mean, we've done the 3 laws, so I guess next is just doing some problems. Let's have a look. And some of these won't be specifically using Kepler's laws directly, but you know, just general questions for the chapter as a whole. Now that we've covered Kepler's laws, there's nothing left for us to do in the chapter but do some problems and review. Actually, we might do a problem where we use this result that we got along the way. That'll be something somewhat new that we can look at. But yeah, let's begin. So, first problem I'm seeing here says a satellite moves in a circular orbit around Earth at a speed of 5,000 meters per second. Oh, actually, before we do this one, already used the backside of that. Let's grab a new sheet. Before we do that, let's talk about geosynchronous orbits. This one is actually not from the problem section of my book, but from the example section. It says, from a telecommunications point of view, it's advantageous for satellites to remain at the same location relative to a location on the Earth. This can occur only if the satellite's orbital period is the same as the Earth's period of rotation, which is 24 hours. At what distance from the center of the Earth can this geosynchronous orbit be found? It is at a specific distance. If you want a specific period, there's a specific distance tied to that. And also, part B is asking what's the orbital speed of the satellite? Because in order to stay at that distance and orbit in that amount of time, it needs to stay at a specific speed. Now, that's not saying that this is the only 24-hour orbit that you can have. It's just the only one that... Actually, wait, let me think about this. Would it be? Oh, well, I guess it would be. Because otherwise it's not going to be a circle anymore. Okay, forget what I was about to say then. I almost ended up putting my foot in my mouth. Alright, so we have the Earth. And here's just some random continents. If you came here for a geography lesson, you've come to the wrong place. And here's a satellite. Here's how I draw my satellites. Take it or leave it. I'm not going to draw the whole thing. We'll just call that a satellite. And we want it to have a 24-hour rotation period. We want it to have an orbital period of 1 day. And we need to figure out at what distance must this be. Okay, so you could just go ahead and use Kepler's third law directly here. You could just say t squared equals 4 pi squared over big G big M times r cubed. But usually my approach to these problems, because again, I don't memorize Kepler's third law, I don't memorize this, or rather I don't memorize this result over here. The one I do remember off the top of my head is this, because, well, this one's easy. It's just t squared over r cubed equals t squared over r cubed, or the reciprocal of it, if that's what you prefer. That one's just easy to remember, so even if you weren't trying, you would probably have that committed to memory. But for the other one, for the single orbiting object version of it, I wouldn't bother trying to remember all this. I wouldn't bother trying to remember, is the 4 pi squared in the numerator or in the denominator? Because you're used to G and M being in the numerator from Newton's law of universal gravitation. You can easily get yourself mixed up, especially if you also get mixed up on, is it r cubed on the left-hand side of it, on the left-hand, I can't talk today, on the left-hand side of the equation, or is it t squared on the left-hand side of the equation? All possible points of confusion. You remember that t squared is part of it and r cubed is part of it, but you don't necessarily remember the order. It's very easy to confuse yourself and get mixed up. So I just like to redo everything from first principles. I like to just redo everything. Once you do this enough times, it's really quick. It does sound like it might be a chore to do it this way every time, but once you've done it a few times, it's really, really quick. So the net force on the satellite is the force of gravity, which is big G, mass of planet, mass of satellite, over the distance squared, equals the centripetal force, because in this case our net force is perpendicular and always perpendicular to the tangential velocity of the satellite. We're assuming a uniform circular orbit here, so is equal to mv squared over r. Thankfully, the mass of the satellite doesn't matter. They didn't give us the mass, so that's good. We can cancel 1 power of r. We've got g big M over r equals v squared. Okay, we can actually solve part B once we have r. So keep that in mind. Actually, we could probably do that in the next step. So the next thing you want to pull is v equals total distance over total time. If the total distance is 1 orbit, then the total time is 1 period. The period of this orbit, by design, we want it to be 24 hours. And 24 hours, I guess we want to convert that to seconds. So it's going to be 2 pi, well, actually, we'll hold off on that. Let's just plug in 2 pi r over t for our v. So g big M over r equals 2 pi r over t all squared. G M over r equals 4 pi squared r squared over t squared. Multiply the r over to the right and move everything else to the left, so you get gm times t squared over 4 pi squared equals r cubed. And you know all this information. The t you have to convert, so t equals 24 hours. Let's convert, and let me switch colors while I'm at it. Let's do this one. So every 1 hour is equal to 3,600 seconds. And if you don't remember it's 3600, that's okay. You can do 1 hour is 60 minutes and then do 1 minute is 60 seconds. You can do it in 2 steps if you like. I was about to do a second step anyway. So 24 times 3600, I believe it's 86,400. Yep, 86,400 seconds. Equals 86,400 seconds. Okay, plug that in for big T over here, and we know all of our other values, or at least we can look them up in data tables. So big G is 6.673 times 10 to the negative 11. If you prefer just 6.67 times 10 to the negative 11 because, you know, it rhymes, it's easier to remember, then by all means go for that. You don't need to worry too much about your sig figs in this course. The Earth, 5.98 times 10 to the 24. The reason I remember the one for Earth is because, well, 10 to the 24, there's 24 hours in a day on Earth, so that helps me remember that one. Over 4 pi squared equals r cubed, so to get r, I just need to take the cube root of all this. Let's see, so if you don't have the kind of calculator that that lets you actually put in the index of the square root, then you can just take this number and then raise it to an exponent of 1/3. You can just raise it to an exponent of 1/3. So I'm going to do 6.673. Whoops, that's not a point. 6.673 times 10 to the negative 11 times 5.98 times 10 to the 24 over 4 pi squared. Remember to use parentheses when dividing by 4 pi squared, or else your calculator will divide by 4 and then take the result and multiply it by pi squared, which would be incorrect. I've warned about this a number of times, but it bears repeating. So if I do that, I get 1.01079 times 10 to the 13 if I take the cube root of that. So if I take, let's see, previous answer raised to the 1/3. Let me show you on my calculator. That's what I'm doing over there. Can you see it? Yeah, that should be showing pretty clearly. I've noticed in the footage when I just lay it on the paper, it's not always the clearest it can be, so hopefully raising it up a little bit helped. And I'm getting 21,621.58 since I converted my time units to seconds and I used kilograms for my mass units for the Earth, and big G is just in its standard units, whatever we got for it last time. I should have radius in meters now. That should be 21,621.58 meters. 21,621 R equals 21,621.58 meters. Gotta make sure I remember to turn my calculator off every time I'm done with it. I was with a student the other day and it just turned off in the middle of me typing things into it. Fortunately, I had a backup calculator, but you know, it has the little solar thingies. I guess I just don't put it in sunlight enough. I don't get direct sunlight through this window. At least not a lot of it. Anyway, now that we have R and it's actually in a pretty reasonable range. Well, that's not the right word to use. Keeping it in meters gives you a pretty reasonable number, but if you wanted to convert it, I guess we could also say it's 21.6 21.6 kilometers, right? Move the decimal 3 places. Yeah, 21.6 kilometers, which is 21.6 kilometers to miles. So that is about around like 14 miles. Wait, actually, is that reasonable? I guess it's a pretty low altitude orbit. Well, that's why I never say that my drawings are to scale. Oh, I think I did do something wrong. Because they're getting a different answer. What did I do wrong? Oh, I forgot to multiply the t squared. See, this is why it's good to develop that habit of asking yourself, are the numbers I'm getting reasonable? This is incorrect. I forgot to multiply by 86,400 squared. There we go. So multiply this by 86,400 squared, and that's 7.5455 times 10 to the 22. Take the cube root of that, so raise it to the 1/3 power. Okay, there we go. Now we're getting a more absurd looking number. Now we're getting R equals, let me switch my calculator to scientific notation mode because I don't want to write out all those digits. Okay, 4.22568. I'll just round it to 4.226. 4.226 times 10 to the 7th meters. Okay, that's better, because I was about to say, that's not reasonable at all. That would be like inside the Earth, because the radius of Earth is 6.38 times 10 to the 6, even if you don't remember the 6.38 part. If you remember the 10 to the 6 part, this is less than even 1 times 10 to the 6. You do not need to memorize the mass and radius of Earth, or the mass of the Sun or Moon, or the distances between any of those objects, but it does help if you remember at least, what power of 10 goes with them. Roughly, it helps you catch mistakes like this. Aren't you glad I keep advocating for best practices like asking yourself after you're done with a problem whether or not the results actually makes physical sense, whether or not it feels reasonable, just kind of trusting your gut? I mean, you can only trust your gut so far in physics, because there are some things that you discover in physics that just defy your intuition. So maybe trusting your intuition too much is also a bad thing, but at the very least, taking pause whenever something challenges your intuition is worthwhile, because either you catch a mistake or you question it and learn something new that helps you kind of readjust your expectations, and maybe your intuition will be sharper the next time as a result. But now I'm rambling. Let's move on to the second part of this question, which was, what is the speed of this satellite. So that, now that we know r, we can find it pretty easily. Actually, we can find it without even knowing r. So without knowing the value of r, all you have to do is rearrange this equation over here. Rearrange this and solve it for r. R is equal to Vt over 2 pi. R is equal to multiply the t over and divide by 2 pi is equal to Vt over 2 pi. Or Tv over 2 pi. I guess if you really wanted to memorize this, I don't think you should, but if you really wanted to, if you already studied everything else and you just want to do something extra because you want some additional advantage and you wanted to memorize this, then I guess you would actually want to write it as TV instead. R equals TV over 2 pi. Like, imagine sitting in front of the TV and watching your favorite TV show over a meal of 2 pies. That sounds like the kind of day I would like to have after all this work I've been doing for these past few weeks, but then again, I don't think I could handle 2 pies. I don't eat that much food to begin with. If I ate even one whole pie, I would probably end up vomiting a few hours later. Anyway, now that we have this, we can rewrite this over here. So we can take gm over r equals v squared. We can rewrite that as v squared equals gm. So we're taking this over vt over 2 pi. Take this and multiply it over to the right hand side and we get gm equals, I guess that'll be v cubed t over 2 pi. Oh, actually, all we needed to multiply was the v. That's okay. We did it in 2 steps instead of 1. Multiply the 2 pi back over and divide by the t. And you get 2 pi gm over t is equal to v cubed. And then if I take the cube root of that, v equals the cube root of 2 pi 6.673 times 10 to the negative 11 5.98 times 10 to the 24 over 86,400. We're already 1.5 hours in, and I thought this was going to be a short stream. Oh well. 2 pi times 6.673 times 10 to the negative 11 times 5.98 times 10 to the 24 divided by 86,400. Fortunately, our denominator this time is uncomplicated. That's 2.90194 times 10 to the 10, and if I take the cube root of that, if I take that to the 1 over 3 power, then I get 3.073 times 10 to the 3, or 3,073 in meters per second. Okay, they got 3,080. That's just differences in rounding. That's just differences in rounding, so I'm not worried about that. So I'm getting about 3,073 meters per second. And yeah, getting something in the thousands of meters per second for satellites is pretty reasonable, but that's not something you would recognize right away. You would actually have to do enough of these satellite problems, and then you would just kind of start noticing a pattern that their speeds tend to be somewhere around the thousands of meters per second. That's not intuition that you would have before doing a good number of practice problems in this chapter. But now that we have that out of the way, let's do some of the actual proper problems of this book, instead of a pre-worked example where somehow, even though the answer was already there in front of me, I still almost made a terrible mistake. Okay, so it was, right, a satellite moves in a circular orbit around Earth at a speed of 5,000 meters per second. There we go. Speeds of satellites tend to be in the thousands of meters per second. What did I just say? It says determine the satellite's altitude above the surface of Earth. Be careful with that wording. And part B, the period of the satellite's orbit. And it better not be geosynchronous, because for a geosynchronous orbit, you'd have to be moving at 3,073 meters per second, approximately. If you're moving too fast or too slow, well, actually, let's talk about that. I'll do that after the problem. I'll do that after this problem. And come to think of it, can I squeeze this problem into this empty space over here? I'm going to try it. We can use this same illustration from before, and actually a lot of the same equations from before. So speed is 5,000. Determine the satellite's altitude above the surface of Earth. So determine r and then subtract the radius of Earth from that. That subtraction step is what a lot of students forget. I warned about this last time. I'm warning about it again because it is a very, very common mistake. Even when you know it, it's just very easy to forget because you're rushing through the problem. So even students who understand this idea really well, it's not a lack of understanding. It's just a lack of good habits. It's a lack of checking your work because you're in a hurry to try and get things done under a time limit, which, I mean, is kind of stupid when you think about it, but that's the education system we have. It's not like when you're working the actual job at NASA, you're under crunch 24/7. Sure, there are some emergencies where being faster would help, but one would hope by the time you encounter an emergency, you would be, whoever's responsible would have already had enough experience that they would just naturally be that fast without even breaking a sweat. Yeah, radius of the planet. I'll just call it big R in case we need to use this illustration again for a different planet later. Oh, who am I kidding? I'm probably going to redraw for future problems. Anyway, we have V satellite, I'll just call it VSAT, is equal to 5,000 meters per second. And we can just use this, actually, to solve for R really quickly. Multiply by R, divide by V squared. So we get R equals GM over V squared. R equals big G, big M over V sat squared. I guess we'll call this R sat then. And we do 6.673 times 10 to the negative 11 times 5.98 times 10 to the 24. I almost want to store this product in my calculator just so I don't have to type it every single time. That might not actually be a bad idea on the test. I mean, don't cheat. I know they don't make you clear your calculator memories anymore, but if you have to resort to that, why are you even here? I do not condone cheating. I've heard all the justifications. Oh, the other people are cheating and I'm just making up for that. No, no. Beat them without cheating. That's the best thing you can do, is humiliate the cheaters as thoroughly as possible by outdoing them even when they cheat. That's what I would rather do. Anyway, dividing by 5,000 squared. And I guess I'll switch back to scientific mode. That's another thing I don't really like too much with this calculator. I have another calculator that automatically just kind of decides what the appropriate mode is, normal notation versus scientific, but, well, this one does too, but you have to go really, really far. So I'm getting 1.596 times 10 to the 7. That number looks kind of familiar. R sat equals 1.596 times 10 to the 7 meters. I'm going to rewrite this as 15.96 times 10 to the 6 meters. And the reason I'm going to write it that way is because now I need to subtract the radius of Earth from it. So altitude, h, is going to equal radius of the satellite orbit minus radius of Earth. And if I keep both of them, the radius of Earth is 6.38 times 10 to the 6. So if my satellite radius is also written as times 10 to the 6, I can just do a direct subtraction. I can do 15.96 minus, for Earth, it's 6.38. Both of those are times 10 to the 6. I can factor it out, so I don't have to write it twice. How do you like that strategy? 15.96 minus 6.38 is 9.58. Is 9.58 times 10 to the 6. So the other, I guess, soft skill that you want to develop for this chapter, now that we're starting to see a lot of scientific notation, is practice just strategies. Pay attention to the kinds of things that you can do with this times 10 to the whatever part of your numbers to make things easier for yourself, and see what you can get away with and not having to type into your calculator every time. Like, one thing you could do, and one thing I would do if I was just doing this, quietly for my own reasons instead of teaching a class, is I would go ahead and mentally combine the 10 to the negative 11 here and the 10 to the 24 and just write that somewhere to the side as 10 to the 13 at the end. I would just combine all my powers of 10 into 1 at the end instead of having to use the times 10 button every single time I have one of these really small or really large numbers. Things like that. And then if this happened to be a multiple of 3, which it's not, but if it was a multiple of 3 and I was taking its cube root, I would just know to divide the exponent by 3 and be done. And I could skip putting that part into my calculator in the first place and just put all the other numbers in and tack on the 10 to the whatever at the end. If you can just make that one of your practice goals, is learn how to work with powers of 10 just mentally, and see how much of it you can remove from the calculator process and do by hand, or mentally rather, so that you don't have to spend as much time because those extra button presses on your calculator for scientific notation do add up. Even if they don't add up to that much in time, they do add up in just frustration and irritability, which are not good for you during an exam. You have to consider the psychological cost of your less efficient methods, as well as the, material time costs. But that's enough test-taking advice. Let's take a look at part B, which says determine the period of the satellite's orbit. So now that we know this is 9.58 times 10 to the 6 meters above the surface of the Earth, what is the period of the satellite's orbit? Well, since we know r, we can just do 2 pi r over v. We can rearrange this into 2 pi r over v and solve for period that way. Another way we could solve for period is, let's see, without referring to the radius at all, we could do I actually have one here that doesn't refer to radius at all? Doesn't look like it, but I can make one. Actually, wait. Yes, I do. Yes, I do. We have this from earlier, right? When I rewrote r equals vt over 2 pi, we got rid of the r, so if we did this, solve for t, so I would multiply the 2 pi and divide by v cubed to get t. Yeah, so I could do t equals 2 pi big G big M over v cubed. And that way I can avoid plugging in a number that I had to calculate just in case my calculation was wrong. The thing that I have warned about how many times during this course now. I didn't even bother counting, but I'm sure someday somebody is going to go in the comments section and start posting those count totals, because yes, there are people who do that in YouTube comment sections. I've seen it. And then there are those who just comment daily, and they're like, day 1 of asking the owner of the channel to do some impossible thing that they'll never do, like it's some sort of dare, or whatever it is that they're keeping count of. There are people on like Let's Play channels who keep track of like how many times the Let's Player failed a mission or died in the game or whatever. I'm sure it'll only be a matter of time before I get one of those statisticians showing up in my comment section. Perhaps it could be you. Imagine the earliest comments on this video being that type. That would that would be a nightmare. Well, I mean, it wouldn't be a nightmare, but it's not what you would expect. I'm rambling too much today. That's why it's almost 2 hours when I thought we would be done in 2 hours or less. I guess it's a good thing that I blocked out enough time for the usual duration of these streams. So 2 pi gm over v cubed. Let's see, 2 pi times 6.673 times 10 to the negative 11 times 5.98 times 10 to the 24, whoops, times 10 to the 24, there we go, divided by 5,000 cubed, and I get 2.0058 times 10 to the 4. 2.0058 times 10 to the 4. That would be in seconds. Not very reasonable. We're talking about, what, 20,000 seconds? We don't know how much time that is. Let's try and divide by 3,600 to get that in hours. In hours, that's 5.57 hours. Now that is much more comprehensible to the human mind. That is much more relatable to the human experience. So t is also equal to about 5.57 hours. That would be a reasonable unit of time to use here. A little more than 5.5 hours, which does sound pretty reasonable for a satellite. Definitely sounds reasonable. Is it at a smaller, let's see, 1.596 times 10 to the 7 compared to our geosynchronous orbit, which was at 4.226 times 10 to the 7. Yeah, it makes sense. It's a smaller orbital radius, and as we know, a smaller orbital radius has to come with a smaller period. So it does make sense that it's less than 24 hours. We know that lower radius is lower period because of Kepler's third law, t squared over r cubed equals t squared over r cubed. If the r cubed is smaller, then the t squared has to be smaller as well, so that that ratio remains constant. Now we can finally move on to another problem. Do I still have? Yeah, I still have the backside of this sheet, so let's get started on that. Let's see, is this one any good? We've got a satellite in circular orbit. Okay, in units of Earth radii this time. Okay, this is an expression problem. So it says we have a 600 kilogram satellite in a circular orbit around Earth at a height above Earth equal to Earth's mean radius. So here's Earth. Here's our satellite again. And I guess I didn't draw this to scale. Its height above the Earth is 1 Earth radius. Its altitude is 1 Earth radius. And this is another Earth radius. As you can see, my scale is way off, but let's pretend that these two distances are drawn equal. So the total orbital radius is 2 big R E. Once you realize that, the rest of the problem pretty much solves itself. The mass of the satellite is 600 kilograms, but that probably won't matter. I'll write it down anyway, just in case we do end up needing to use it. So it says, find the satellite's orbital speed, the period of its revolution, and the gravitational force acting on it. Okay, to know the gravitational force acting on it, you would need to know its mass. So at least it'll be useful for that third part. But part A, the satellite's orbital speed. Well, if we're solving for v, then we can just do force of gravity equals your centripetal force. So big G m over r squared equals mv squared over r. The m's cancel out. 1r cancels out, and there you go. We have v immediately. See how quick that is? This is why you are much better off remembering the derivation process. Gm over, this is 2 Earth radius, is the radius of the orbit. equals v squared. Therefore, v is going to be the square root of all that. And big M here would be the mass of the Earth, of course. So 6.673 times 5.98 times 10 to the 13. I just combined the 10 to the negative 11 and the 10 to the 24 there. We talked about this. And then that's divided by 2 radius of Earth, so that's a 10 to the 6. Okay, 10 to the 13 over 10 to the 6 is 10 to the 7. So there's that. So now it's divided by parentheses 2 times 6.38, close parentheses. Okay, and I'm getting 3.127 times 10 to the 7. I'm getting 3.127. Oh, wait, I forgot to square root. I was about to say that's way too big. Okay, 5.592 times 10 to the 3. That's better. 5,592 meters per second, give or take. I would probably round this to 5,600 because at this point we're probably not going to be getting precise down to the nearest whole meter per second or even the nearest 10 meters per second. I would probably round this to the nearest 100 meters per second. As long as you're not being too crude with your rounding, the AP graders aren't going to concern themselves with that too much. Save your focus on sig figs for AP chemistry. Or if you have one of those AP physics teachers that's strict about sig figs, I guess. So that's part A. Part B, the period of its revolution. So we can start with this and go v equals 2 pi r over t. We can do v equals 2 pi r over t. So the square root of gme over 2 re, all of that is under the square root, is equal to 2 pi little r, which is equal to 2 Earth radii, over big T. And now we can just solve for t. So multiply by t, divide by all this stuff. So we get t equals, I guess that'll be 4 pi re over the square root of g me over 2 re. You know what? Why not? Let's actually reuse a calculated result. I know. Horrible sin, right? Complete hypocrisy after everything I've said, but I mean, we're literally just plugging in the same numbers anyway. So yeah, this is just going to be the 5592 we got earlier. 4 pi times 6.38 divided by 5592, and then that times 10 to the 6. I didn't forget, I just left it for the end. And that's 1.4337 times 10 to the 4, or 14,000? Yeah, 14,337. About 14,337 seconds. Or if we divide that by 3,600, about 3.98 hours. About 3.98 hours. Does that make sense with what we said earlier? A geosynchronous orbit is, yeah, still way farther than that. Way farther than 2 Earth radii, because a geosynchronous orbit is times 10 to the 7. It's not quite 10 times an Earth radius, more like, I want to say it's closer to maybe 7 times an Earth radius. So yeah, less than 24 hours still makes sense. And then part C, find the gravitational force acting on it. I'm skipping that. You guys know how to do that. It's just literally plug in the numbers into Newton's law of universal gravitation. Gmm over r squared. Your second m is 600 kilograms, and the rest we already know. Big G, mass of Earth, 600 divided by 2 Earth radii squared. Remember, when you square that, you're squaring the 2 with it. That's a common mistake that people make. So many common mistakes in this chapter. The chapter is not particularly hard. It's just that there are a lot of opportunities to make really easy mistakes. Next question, we have Io, a satellite of Jupiter, has an orbital period of 1.77 days and an orbital radius of 4.22 times 10 to the 5 kilometers. From these data, determine the mass of Jupiter. These data, huh? Is data a plural? Well, yes it is. You might remember what I said back in the momentum chapter, that the plural of momentum is momenta. Well, data is also a plural. Data is the plural of datum. Yeah, data is a plural. If you think about it, you've never actually used it as a singular, have you? You've never said a data or one data or something like that. Usually you refer to pieces of data, if anything. That's the closest you get to cutting data down into single units, linguistically speaking. I'm not beating the English tutor allegations, am I? Anyway, so Io, a satellite of Jupiter, and yes, a satellite can be natural, in case you don't remember your Earth and space science vocabulary. The word satellite refers to both man-made satellites and natural satellites. Anything that's orbiting a planet is a satellite of that planet, whether it's a natural one like the moon or an unnatural one like the satellites that we launch into space. So yeah, Io, a satellite or moon of Jupiter to be more specific, has an orbital period of 1.77 days and orbital radius 4.22 times 10 to the 5, and we can use this information to determine the mass of Jupiter. So T is 1.77 days. This is T for Io, and R of Io, the orbital radius, is 4.22 times 10 to the 5 kilometers. 4.22 times 10 to the 5 kilometers. This is mostly an exercise in converting units. So if we want the mass of Jupiter in kilograms, our standard units, then we need everything else to be in the standard units. as well. So 1.77 days, we need to convert that to seconds. So t is 1 day is 86,400 seconds, if you remember from earlier. If you don't, just multiply it by 24 to get it in hours, and multiply it by 60 to get it in minutes, and then multiply it by 60 again to get it in seconds. We know how to convert units by this point. 1.77 times 86,400. That's 1.52928 seconds, or times 10 to the 5 seconds, or 152928 seconds. And then radius of Io, it's in kilometers. I need to convert it to meters. Fortunately, a kilo is just 1,000 or 10 to the 3. So this is a quick one. It's just 4.22 times 10 to the 5 becomes 10 to the 8. And now it's in meters. Done. Okay, find the mass of Jupiter. Well, if Io is orbiting Jupiter in a circular orbit, then the force of gravity is the net force acting on it, and it points towards the center of the orbit, towards the core of Jupiter, or wherever the center of gravity of Jupiter happens to be. And that means it's equal to the mass of Io times its tangential speed squared over the radius of its orbit. We cancel one radius. We cancel the mass of Io. Multiply one radius over to the right. Divide by big G, and there you go. The mass of Jupiter is equal to, oh, wait, we don't know V. That's okay, we can fix that. So that's going to be m Jupiter times V squared. Well, V is equal to, speed is equal to distance over time. If the distance is 2 pi r, then the time is 1 period, 1 cycle. So mass of Jupiter equals, let's see, it was V squared times R divided by big G. And then if we expand on that, V squared is going to be 4 pi squared R squared over T squared. So 4 pi squared R squared, the R squared and the R that we have out there will combine. Let's do it one step at a time. And then that's over T squared, so there's going to be a T squared down in the denominator times big G, and then that simplifies to 4 pi squared over big G, that looks a little bit more familiar, times R cubed over T squared. Okay, now it's looking more like what we had at the beginning. Well, maybe not the beginning of today's stream, but you know what I mean. Okay, 4 pi squared over big G times 4.22 cubed times, that'll just be 10 to the 24. I'll leave it on the side. Let's see, so 4 pi squared times 4.22 cubed divided by 6.773. Almost forgot the value of big G for a second there. And also divided by 152928 2928 squared. Okay, and I'm going to multiply that result by r cubed gives me 10 to the 24, g gives me 10 to the negative 11, so that's going to be 24 minus 11, that's going to be 10 to the 13. So that's 1.873 times 10 to the 5, or 187,000, I guess. Wait, that doesn't make sense. The mass of Jupiter should be way bigger than that. What did I do wrong? What did I do wrong this time? Because that is way too small. Let's see, 4 pi squared times 4.22 cubed over 6.673. Oh, I did mess it up, didn't I? I said 6.77, it's 6.673. Okay, so that's one thing, but I don't think that was the major issue here. And also divided by 152928 squared. And then for exponents, yeah, 10 to the 8 cubed is 10 to the 24. Oh, dividing by 10 to the negative 11 is adding. That's what I did wrong. So it's not 24 minus 11 to get 10 to the 13. It's 24 minus negative 11, 10 to the 35. That's what it is. Okay, take that times 10 to the 35. I guess I should take my own advice and practice with my powers of 10 and laws of exponents. But hey, at least I'm catching my mistakes. So that gives me 1.901 times 10 to the 27. That sounds better. 1.901 times 10 to the 27. Whoops. What am I doing? Let's try that again. 1.901 times 10 to the 27 kilograms. This sounds more believable. The mass of the Earth is something times 10 to the 24 kilograms, so this is on the order of about 1,000 times more than the mass of the Earth. That I find to be more believable, given what we know about how massive Jupiter is. It is the biggest planet in the solar system. Of course, size isn't everything. It is mostly gas, but it's a lot of gas. Any other questions on that? Nope, it doesn't look like it. Okay, next one says... I guess we could do that one. Okay, we'll do both of them, and then we will wrap up with that. And actually, I should mention this now. One of the questions I was planning on doing for circular motion was a question that I found out I already did. I found out that I already did it in a past video. And in fact, it's the same video I linked to in the previous stream. I linked it in the iCard, and I linked it again in the description for a set of problems involving, like, comparing planets of different density. That was just a section of that video. But if you go to that video, and go to the 45-minute mark, I think the title of the video was something like some challenging circular motion and gravitation problems, something like that. It was from almost a year ago at the time of this recording. So yeah, if you're having trouble finding it, just go back to the previous stream. What part is this? Is this part 23? So go back to part 22, if I'm getting my numbers right. Hold on, let me see. What part are we on? Yeah, we're on part 23, so if you just... Wait, great, now I have to rearrange my screens. Okay, that's better. So, yeah, if you go back to part 22 and just go to the link in the description, it's set to take you to a specific point in the video for a specific type of question, but if you just go back to, I think it was around like the 45-minute mark, you will see a certain circular motion problem that is algebraically difficult. It requires some clever use of algebra and trig in order to do a certain part of the problem, and I think it's a very important problem for you to see, but I am not going to do that today because we're kind of going past how long I expected this stream to last. So yeah, you can go back to that video. In fact, you might just want to watch the whole video because there's a good number of problems in there. And again, they are kind of challenging problems, so well worth it. I'll just keep things to planetary motion today. So 2 more problems and then we'll wrap up and we'll talk about what is to be expected next time. So this one says a satellite has a mass of 100 kilograms and is located at 2 × 10⁶ meters above the surface of Earth. That is an altitude, that is a height, that is not an orbital radius. We need to add the radius of Earth to that to get an orbital radius. So it says, what is the potential energy associated with the satellite at this location? And second part says, what is the magnitude of the gravitational force on the satellite? The second part is really easy. You just multiply. The only hard part about it is remembering to add the altitude to the Earth radius to get your R. Once you have that, it's just plug in the numbers. We already did something like this in a previous question, so I'll skip that part. But let's go ahead and figure out what the potential energy is, because if I remember correctly, there's an interesting observation here. Actually, wait, no. That would also be just a matter of plugging in. Oh, just r to the first power, not r squared. Almost made a mistake there. Yeah, that one's also just plugging in values. Okay, never mind, we'll skip this one. We'll skip this one entirely. I mistook it for something else. Okay. We're still going to use this anyway for this next problem. So, next problem says, a satellite of mass 200 kilograms is launched from a site on Earth's equator into an orbit 200 kilometers above the surface of Earth. Assuming a circular orbit, what is the orbital period of this satellite? And then part B, what is the satellite's speed in its orbit? And then part C, what is the minimum energy necessary to place the satellite in orbit, assuming no air friction? And this is reminding me of something that I forgot to talk about earlier, so I need to remember to do that after this problem. Okay, so 200 kilograms for the satellite mass, msat equals 200 kilograms. It's launched from a site on Earth's equator into an orbit 200 kilometers above the surface of Earth. So height equals 200 kilometers, or 200 times 10 to the 3 meters, or 2 times 10 to the 5. 2 times 10 to the 5 meters. Or, better yet, 0.2 times 10 to the 6. Why 10 to the 6? You might remember from an earlier problem, because if we're going to add this to the radius of the Earth, which is already on the order of 10 to the 6 meters, this will make it easier to just add them right away. In fact, let's go ahead and do that. Radius of Earth is 6.38 times 10 to the 6 meters. So the orbital radius of the satellite is going to be 6.38 plus 0.2 is 6.58. 6.58 times 10 to the 6 meters. So there's that done. So first part was asking what is the orbital period of the satellite. Do I have anything here? I guess I do. I'm gonna square this. I'm gonna take this and square it. Actually, no, wait, I don't want to use this because it uses a specific... Okay, never mind. I'll just start from scratch. So G mm over r squared equals mv squared over r. Cancel an r, cancel an m. V is equal to 2 pi r over t, and if I square it, that's 2 pi r over t all squared. So that's G m over r equals 4 pi squared r squared over t squared. Put t squared over on the left and divide and multiply everything else over to the right. So t squared equals 4 pi squared over big G, big M, and then the r and the r squared just combine into an r cubed. Okay, there we go. Once you do it enough times, you can do it that quickly. Actually, probably even quicker than that. And then square root both sides and get your period that way. So 4 pi squared. By the way, if you're just estimating, like on the multiple choice, and you don't want to bring out your calculator, pi squared is approximately 10. So, you know, if you're just kind of trying to do a quick guess and check and you're looking at the multiple choice answers and you just want to figure out something real quick that's close enough and then pick the answer choice that's the closest number, that's a little strategy tip for you. But I wouldn't go... I wouldn't get too trigger happy on trying to use pi squared as approximately 10 because it's not that close. Pi squared, let me put it in my calculator. Pi squared is 9.87 approximately. So I guess it's, interestingly enough, a pi squared is approximately g, little g, the 9.8 we've been using up until this chapter. Almost. But yeah, that's just an interesting factoid about pi squared that you might be able to take advantage of in a few situations. Again, don't go into your tests expecting to use this a lot, if at all. But just a little thing to know. So 4 pi squared r cubed, so 4 pi squared times 6.58 cubed divided by 6.673 and also divided by 5.98 gives me 281.848. And then for my powers of 10, we've got 10 to the 6 cubed is 10 to the 18, and then 10 to the negative 11 and 10 to the 24, that's 10 to the 13. So 10 to the 18 over 10 to the 13, that's going to be 10 to the 5. So 281, I'm just going to multiply this result by 10 to the 5, and that's 2.818 times 10 to the 7. So t squared is about 2.818 times 10 to the 7, give or take. And if I take the square root of that, I get 5.309 times 10 to the 3. T is about 5.309 times 10 to the 3, and that's in units of seconds. And I guess if you want the units on this, it would be in seconds squared. Not a very comprehensible number. 5,309 seconds is a little over an hour, so it's not as terrible as some of the other absurd numbers of seconds we've seen today. But still, let's divide it by 3,600, and that's about 1.47 hours. Equals about 1.47 hours. Okay, part B. What is the satellite's speed in its orbit? What is the satellite's speed in its orbit? Well, for that, we can just go back to this over here. When we eliminated 1m and 1r, we just had v squared left. So let's use that. V squared equals gm over r. So if I just take the square root of that, so v equals square root of gm over r, that's going to be 6.673 times 5.98 divided by 6.58. 6.673 times 5.98 divided by 6.58, and that's going to be 6.0645, and then we have 10 to the 13 from G and mass of Earth, and divide by 10 to the 6 from our satellite, so 13 minus 6, 10 to the 13 over 10 to the 6, that's 10 to the 7. Or I can do this, so equals square root of 6.06452 times 10 to the 7, or I can make this an even exponent by just moving the decimal one place. So that's 60.6452 times 10 to the 6. And why do I want to make this an even power of 10? Because now I can square root it easily. If I pull it out of the square root, it just becomes 10 cubed. So square root of 60.6452, whatever that is, times 10 to the 3. So that's 7.7875. I'll round it to 7.79. So I'm getting about 7.79 times 10 to the 3. And that is in meters per second, which is in the thousands of meters per second, which, as we've established earlier, is pretty reasonable for satellite speeds around the Earth. So I believe it. I'm not seeing anything like glaringly wrong with it. Part C, what is the minimum energy necessary to place the satellite in orbit, assuming no air friction? Here is the part where my question from last time is finally going to come into play. Last time, I asked, why is it that we prefer to launch our rockets in the United States from Cape Canaveral in Florida? Why that place specifically? I guess you could also make it work in Texas, maybe, in some parts of Texas, but what's special about Florida? Well, Florida is pretty far south, about as far south as you can go in the United States. And why that matters, well, you might remember that the problem mentioned here that the rocket was launched from a site on Earth's equator. I'm hinting at it, but let's write out the math and see what's going on. So I can do, well, we're going to burn rocket fuel. We have to burn rocket fuel to get into the air. So there is some non-conservative work being done on the satellite by the force of, I guess you can call it thrust from the engines. So there is some non-conservative work. There is some initial kinetic energy, KE initial, plus initial potential energy initial, plus some non-conservative work equals your final kinetic and potential energy. Okay, what is the kinetic energy? Well, we kind of did that earlier, or at least we talked about it a little bit. If you want kinetic energy, you have the v squared here. All you have to do is multiply by 1/2 m. And you get 1/2 gmm over r. So kinetic energy initial is 1/2 gmm over r initial. And potential energy initial is going to be negative gmm over r initial. Just what we wrote up here. Plus the non-conservative work equals kinetic energy final, which is, let's see, 1/2 gmm over r final plus potential energy final, so plus negative gmm over r final. Well, isn't this nice? It looks like our kinetic and potential energies combine really nicely. Now, some of you might be saying, wait a minute, isn't the initial kinetic energy 0? Isn't the rocket launched from rest? No. Relative to outer space, did I call it a rocket? The satellite. Yeah, satellite. Anyway, rocket, satellite, it doesn't matter. We're splitting hairs at this point. But the satellite does not have an initial speed of 0 relative to outer space. Its initial speed is, well, it's on a moving planet. I've said this numerous times over numerous parts of this course, but you sitting still right now are not actually sitting still. You are moving at whatever speed the Earth underneath you is moving if you're sitting still relative to, well, your own perspective. So the reason we prefer to launch our satellites and rockets from Cape Canaveral, Florida, is because places that are closest to the equator are going to be moving the fastest on the Earth. If we're looking at, I'll draw it over here since I've got this nice big chunk of space left up here. If this is Earth, and this is the axis of the Earth, and the Earth is spinning this way, then if you're on the north or south poles, all you're really doing is spinning in place. It's like stand up right now and turn around 360 degrees. There you go. You just spun in place. You didn't really travel any distance. So the north and south poles are really bad news if you're trying to launch rockets from there. On the other hand, when you're closest to the equator, you are traveling the greatest distance around the Earth. People that are closer to the poles, someone over here, is traveling a much shorter distance around the axis of the Earth per day as compared to someone at the equator. Someone at the equator travels the whole circumference of the Earth in the same amount of time as someone up here travels the whole circumference of the Earth. So if they both have to travel in the same amount of time, and this person over here at the equator has to travel a much greater distance, then they have to be moving at a faster speed. This is going to be explored pretty much immediately at the beginning of next part, next chapter. We're going to talk about this, and we're going to bring back something that I haven't done in a while, FET simulations, but more on that when we get to next part, whether I do it tomorrow or Sunday, or some later day if my schedule decides to upheave itself. Is upheave even a word? I know upheaval is a word. Anyway. So if you're at the equator, you are moving at a speed of, well, let's see, you're moving a distance of 2 pi times the radius of the Earth in a period of 24 hours. So you actually know exactly what V equator is, or at least you can calculate it, is 2 pi radius of Earth over period of Earth. So kinetic energy initial is not 0. It's not 0. This is an equivalent value. We don't have to actually calculate this and square it and multiply it by 1/2 m. I mean, if you do, it's just going to be equal to this anyway. But yeah, the kinetic energy initial is not 0. So now that we've got that idea out of the way, let's take advantage of the fact that kinetic energy and potential energy have very similar forms in this case. Have very similar forms. The only time when this wouldn't be the case is if there was some other motion relative to the surface of the Earth. So that's something to keep in mind. This could turn out to be wrong if you are talking about something that's already moving relative to the Earth. But at least in this problem, we can take advantage of the fact that they all have a GMM over R in common with each other. This one is positive 1/2, this is negative 1, but everything else is the same between them. So if we factor out the GMM over R, then we're just left with 1/2 minus 1 is negative 1/2. So I get negative 1/2 GMM over R initial plus work non-conservative equals negative 1/2 GMM over R final. I can't really cancel anything here because the non-conservative work doesn't have a factor in common with any of these. So we'll just have to move this over to the right-hand side and solve for the non-conservative work. At least once I move this over here, then I have something I can factor. So let's actually do that, and I'll do it up here. So add 1/2 to both sides, or add all of this to both sides, and I'll factor out 1/2 GMM. So I'll have I'll have work non-conservative on the left-hand side equals 1/2 big G MM times, we have negative 1 over R final, and this once added to the right would be positive 1 over R initial. So I'll do 1 over R initial first and then minus 1 over R final. There we go. So negative 1 over R final is left from that, so that's written over there, and positive 1 over R initial is written there. Okay, and we can now just plug in what we know. Plug in the value of big G, plug in the mass of the Earth, plug in the mass of the satellite, which was given as 200 kilograms. I forgot to write that down. And oh, no, I didn't forget. It's right there. And then 1 over R initial, that would just be the radius of Earth. I'll plug it in a minute, but for now I'll just write it as RE so that it looks nice and clean on my page and so that I don't have to spend as much time writing. And then 1 over R final. R final is what we called R satellite earlier, 6.58 times 10 to the 6. Okay, and that's going to be 1 over a smaller number minus 1 over a larger number. 1 over a small number is bigger than 1 over a larger number. That's how fractions work, which means our non-conservative work would be positive, which does make sense. You do need to put energy into launching rockets. They don't just magically drift off into space just based off of their initial speed at the equator alone. It does help. It reduces the energy cost, but there's still a cost. So let's go ahead and put our numbers together. I think I'm going to do the subtraction part first. So 1 over 6.38, and I guess I can factor out the 10 to the 6. Well, it would be 10 to the negative 6 since it's in the denominator. So yeah, I'll do 1 over 6.38 minus 1 over 6.58, and that's 0.004764. And then multiply that by 10 to the negative 6. So let's go ahead and do that. So I'm getting, for this, I'm getting work non-conservative equals 1/2 GMM times 4.764 times 10 to the negative 9. Since we have a lot of calculation steps, you might have noticed I've been tending to keep more decimal places than usual. That's to help minimize rounding errors at least somewhat. Okay, multiply all that by 1/2 GMM, so let's do the 1/2 GMM. 1/2 times 6.673 times 5.98 times little m was 200 kilograms. Okay, and then multiply that result by 10 to the, let's see, 13, since it's negative 11 from the G and positive 24 for the mass of Earth. And that's 3.9904 times 10 to the 16. So that multiplied by 4.764 times 10 to the negative 9. 4.764 times 10 to the negative 9. And my final result is the non-conservative work is 1.901. 1.901 times 10 to the 8 joules, or 0.19 times 10 to the 9, or 0.1901 times 10 to the 9 joules. 10 to the 9, that is a gig. That is 0.1901 gigajoules. Or if you don't like having a decimal point there, you could go in the opposite direction. 190.1 times 10 to the 6. 190.1 megajoules. A mega is a million, a giga is a billion. But yeah, on the order of a billion joules. And that is our final problem for the day. Now, there was something else I wanted to talk about. What was it? Oh, right. So, why is it that a lot of orbits of celestial bodies seem to be perfect? Right? You have to be moving at the perfect speed, at the perfect distance, with the perfect mass for whatever the orbited object is. Like, how do these orbits even come into being in the first place? What if, the moon was just moving randomly one day and then the Earth just caught it? How did it succeed in catching the moon, for example? How does that work? Well, one, it's not super perfect. It's not super perfect. The average distance between the Earth and Moon is actually changing by a little bit over time. But I'll give you an idea of how it works. So let's say here's your orbited object. Let's say it's the Earth, for example. And here's your orbiting object. Let's say it's the moon, for example. And let's say the perfect orbit is over here. Let's say the perfect orbit is over here. And this thing is all the way out there, a little off from the perfect orbit, and maybe not at the perfect speed. Maybe it's moving over here and it's moving too slow. So over here, maybe it's moving too slow. So it could have stayed in an orbit like this, but since it's moving too slow, what's happening is the force of gravity is going beyond just turning it and staying 90 degrees with it, it's pulling it in. It's tilting it this way, so the path ends up being something like this. Now, as it gets closer and closer, if it's speeding up, then the amount of force required increases. And this doesn't just work for planets, by the way. This also works kind of for cars swerving on roads and stuff like that. It's kind of a self-correcting problem. Not perfect self-correction, but good enough for most purposes in life. You have the force required is always mv squared over r. If the mass isn't changing, then when your speed is too high, what's going to happen is you're going to need more force, and if your speed is too high, what'll happen is you'll drift outwards. You'll drift outwards. And what does drifting outwards do? Drifting outwards, eventually, even if you don't slow down, eventually you're going to reach a point where, since this radius is getting bigger, at some point, whatever force you have here, whatever this net force is, let's say it doesn't change, although it can. It certainly can for gravity because it changes with distance. But let's say it didn't, even if it didn't. Whatever your net force is here, eventually, as your object drifts out of its original circle, the circle that it could have been in had it been moving at an appropriate speed. As it drifts outward, this r is getting bigger, and as it gets bigger and bigger, eventually the mv squared over r does end up being equal to whatever net force you have. If you had, I don't know, maybe it's better to put some actual numbers on this. Let's say you have a total force of, I don't know, 1,000 newtons for something. And you have an object of mass, I don't know, 20 kilograms, let's say. And it starts off at a radius of, let's say it starts off at a tight radius of, let's say, 5 meters. And it's moving, let me see, 20 over 5 would be 4. So I guess 250, anything faster than 200, oh, okay, forget about 5 meters then. Let's make it 50 meters. Let's say it's moving on a circular path of 50 meters. So the appropriate speed would be, or rather the appropriate speed squared would be what? 20 over 50 is 2/5, multiplied by 5, that's 5,000 over 2 is 2,500. So the appropriate speed would be 50 meters per second here. Ideally, you would want to be moving at 50 meters per second in order to make this work. If you're moving at faster than 50 meters per second, you're going to swerve off. This radius is then going to increase. Let's say that this is, for example, 60 meters per second. Let's say that this is 60 meters per second. So you have 1,000 newtons of force, but instead you've got 20 times 60 squared over r. Well, what's going to happen is you're going to keep on swerving out until you are at a distance of, what will it be? I guess we can solve for it. So 1,000 divided, or no, 20 times 60 squared divided by 1,000. So 20 times 60 squared divided by 1,000 is 72. How about that? Also, let me switch back to normal mode because my calculator reported that in scientific notation, which is kind of too much. Anyway, so this I guess this isn't a car, but let's pretend for a minute that this moon around the Earth is actually a car on the road. So this car, now that since it's moving too fast, it's going to drift outward until it reaches a turning radius of 72 meters, and then it won't be perfect because its velocity won't be... Well, actually, let me think about this for a second. No, actually, its velocity will always be tangent to its path. That's just... Yeah, it would just be tangent to some sort of, I don't know, non-circular path up until it gets to the 72 meters. And once it reaches that 72 meter sweet spot, then it starts moving in a nice circular path. Similarly, if it's moving too slow and there's too much force pulling it in, well, then that's just the reverse situation. If it was moving slower than 50 meters per second, if it was moving at 40, so 20 times 40 squared over r, set that equal to 1,000. Let's see what that r would be. So it would just be swerving inward until 20 times 40 squared divided by 1,000, r equals 32. So it would continue moving inward until it reached r equals 32 meters. And then from that point on, it would just continue in uniform circular motion until it's disrupted by some other forces acting on it, of course. So a similar thing happens with planetary motion, except over here it's not going to be super perfect, because while it works nicely for, say, cars swerving in and out of their path, assuming there aren't any barriers blocking them from, swerving their way over to a more appropriate radius, which I guess would happen maybe on open terrain, on like a dirt path instead of paved roads with usually buildings and other stuff in the way, buildings and sidewalks and just some physical concrete lane borders separating different sides of the highway. So yeah, I guess you don't get to see that with cars very much either. But for planets and moons and stars, the issue is the centripetal force is changing while the distance is changing. So you could end up with a case where the appropriate radius for the object's speed is never reached, because the force is changing and the speed is changing is the other thing. The force is changing and so is the speed. So you might just get close to, but not quite to, a circular orbit. So if over here you have the moon moving too fast around the Earth, it'll swerve outward. The force of gravity acting on it will decrease, but hopefully the speed of the moon will also decrease just enough that the moon can't escape Earth's gravitational field. Hopefully, by the time it drifts far enough away for the gravity to significantly decrease, its speed will have decreased enough that it can't quite escape, and then it'll be on a somewhat circular path, although it won't be a perfect circle in all likelihood. But that's the thing, it doesn't need to be perfect. Similar things happen when you're being dragged inward. You can think of the logic in reverse. You can reason in reverse that if the moon is moving too slow, it gets pulled inward it gets sped up as it gets pulled inward, because some of that inward pull is giving it speed. Some of that inward pull is, if it's going too fast, I've messed up this drawing really badly. If it's going too fast, let's say this red is the new too fast initial velocity. Wait, too fast? No. Too fast is the first example that I gave. Hold on. It's been a long day. If the moon was going too slow, then you have more than enough acceleration to keep it in its current circle. In fact, you have this extra acceleration that helps drag it in, but that extra acceleration also gives it more speed, increases the magnitude of its speed, and adds more to this, I guess, perpendicular component of its speed. So it gets closer and it also gets faster, and as it gets faster and closer, eventually the force needed increases. It increases with the square of the speed. So in fact, the increase in speed eventually outweighs the effect of decreasing radius. Hold on, I worded that wrong. Oh my goodness. Today was the wrong day to do this. What is my brain doing today? Major brain malfunction. So the speed is increasing as you get closer, and the radius is decreasing. Both of those factors together will lead to an increase in the amount of gravitational force necessary to keep this thing in orbit. But since it is getting closer, that gravitational force is increasing. So eventually what can happen, as long as it's not moving too slow to begin with, what can happen is it'll find a somewhat appropriate orbit. Again, not a perfect circle, but close enough to a perfect circle. Like it might crisscross its own path a few times here and there. If it's going too slow, however, what's going to happen is it'll just kind of spiral its way and just crash into the Earth. Similarly, in the going too fast scenario, if it's going fast enough, it could just circle its way out and just zoom off into outer space, and maybe it'll get caught by some other planet or get swallowed by the sun or something. Who knows? But yeah, those perfect orbits that you see in space are not actually perfect. It's not magic, it's just there is some range of velocities at which the orbiting objects could approach a potential center for their orbit. And if they are within that range, then eventually they will find themselves fitting not super neatly, but neatly enough into some sort of semi-perfect orbit. I'm not sure what more to say about this. I hope, despite all of the major brain malfunction moments I had while explaining this, that you got something out of it, that you gained some understanding from it. And if not, then maybe just reflect on it a little bit, because at least I've put the main ideas out there for you to think about. You can probably reason through this for yourself a little bit better than how I explained it. But I think that'll be it for today. So, next time, which if it's not tomorrow, then I will, well, I already said everything at the beginning, so I don't want to repeat myself for too long, but somewhere between now and Tuesday, expect 2 more parts. Whenever the next part is, whether it's tomorrow or Sunday or maybe even Monday, we will dig into the topic of rotational kinematics, which is something that is often introduced in the circular motion chapter, but I don't like doing that. It does affect some of our circular motion equations. It just gives you another way to do things like calculating centripetal acceleration, but it's not that big of a deal that I felt the need to include it in the current chapter. So that's coming up next time. We're going to talk about the speed of rotation of things that just spin in place, we're going to talk about, basically it's just going to be kinematics all over again. The next chapter, if you've been paying attention and memorizing the equations that I've told you to memorize, which is, even if I didn't tell you to memorize them, it's most of them. In fact, you might be better off remembering which equations I told you not to memorize. But if you have been memorizing most of the major equations of all the previous chapters, this next chapter is going to be really easy for you to digest because, yes, there are a lot of new equations, but most of them are just rotational versions of equations you already know. So if you know your equations well, you're going to have a pretty good time with this next chapter. This next chapter, rotational dynamics, I consider to be the second most important chapter in all of physics. So force, I consider to be the most important. Once you've mastered that, I consider this upcoming chapter to be the second most important. Like, this is the second biggie. If you study nothing else for your AP exam, study force and study rotational dynamics, which I guess would also force you to study energy at the very least. But everything is going to be in this chapter. We're going to have kinematics, we're going to have energy, we're going to have force, we're going to have momentum, we're going to have circular motion. We're going to have it all. We're actually going to have enough information in the very next stream to do accelerated circular motion as opposed to just uniform circular motion. We'll see what happens when, for example, if you're driving in a car on a circular path, but you're speeding up or slowing down, yet somehow managing to stay on your circular path. How does that work? We will have the tools to deal with that next time. So I guess that is it for homework. Just look through the problems listed in the course plan from the OpenStax textbook, which is also linked at the top of the course plan. If you don't know what I'm talking about, see the link in the description. Also in the course plan is a bunch of, I do this for every chapter, but worked examples. I link to a bunch of YouTube videos of a guy doing a bunch of example problems. You might want to look at those if you're still feeling iffy about this chapter. You'll definitely want to do that for this upcoming chapter, especially once we get into like the third or fourth stream of it. It's going to be one of those longer chapters again, I think. I'm imagining at least 4 or 5 streams worth of material. At least if I go at the pace that I would prefer, that should be the case. If I want to speed run it in 3 streams, I suppose I could, but I don't think that's a good idea. Anyway, homework. So, yeah, do book problems, whether it's from your own book or the OpenStax book. If you feel like there's more stuff that you want to learn and review, go check out that video that I linked in the description in the previous stream. I suppose I will link it again. in this one, once I get around to timestamping everything, if you want to just look it up, it's titled something like some challenging circular motion and gravitation problems or something like that. Dropped my calculator. Great. And if you want to read ahead for rotational kinematics, you can do that. It's probably not titled rotational kinematics in most textbooks. It's probably a split between the circular motion and rotational dynamics chapters of whatever textbook you have. So if you're not finding any reference to rotational kinematics, if you're not finding that exact wording in your textbook, that would be the place to look. You are looking for the words angular. If you see angular displacement, angular velocity, and angular acceleration, those are basically the three things we are going to focus on next time. So wherever in your book those are mentioned, that's where you want to read if you're the type of person that likes to read ahead. But that is it for me. Take care, and I will see you in the next one.